Hello again. This is Math 2270 coming to you from the College of DuPage. And the title of this lecture is two take-home problems for the fall of 22 final exam high-stakes assessment. As always, please be attentive while watching this video. By way of introduction, these two problems will count exactly like the numbered problems that you're having in the final high-stakes assessment. And these two problems must be submitted to Blackboard before the end of our final exam testing interval. I'm asking Jesse Hayes Carver to establish a slot on Blackboard for you to upload PDFs of your solution. And again, these two problems will count equally with the numbered problems on the final high-stakes assessment that you will be taking in a brick and mortar testing center. Now, as take-home protocols apply, meaning that you can get help, no one's going to tell you the answer, but you can get help, you should consider this quite an upside opportunity for you. But these are not extra credit, but they're part of the exam. So that if these are not turned in, you missed two complete problems. For your convenience, copies of these PowerPoint slides will be posted to your syllabus tab in Blackboard. The first problem addresses quantitative and qualitative modeling of differential equations. So you consider the following very nonlinear initial value problem. So dy dt is going to be t squared minus y squared whole times sine of y, and y of 0 is equal to minus 1. So in problem 1a, you're to use each of the following techniques: the Euler technique, the Hone formula, three-term Taylor formula, and fourth order Runge-Kutta, and a step size of h equals 0.5 to approximate the value of y at 0.4. And so what your submission should contain a completed matrix looking like this. And you should not round off between steps. Keep all the available digits in a default mode of Excel in the interest of accuracy. And in your final answer below, shown in this table, show each step in the table to 4 digits after the decimal point. So that's the accuracy that we're required. Okay, so that is problem 1A. Problem 1B, and you're to use the same nonlinear differential equation, but use a direction fields program. For example, you could use WinPlot that Jesse Hayes Carver provided to plot the direction fields associated with this differential equation, and use the utility to show the particular solution for a dozen different initial value conditions, including the one that is described in problem number 1. And you're to paste a screen capture of these results here in your submission, and also I expect you to have a narrative where you comment qualitatively on the long-term behavior of these solutions. Again, use complete sentences in your narrative, and your narrative probably should not be handwritten. It should probably be typed. So that is problem number 1. There are parts A and B. Problem number 2 is a modeling problem, and you're to solve this. So assume a coordinate system where the origin is a point where the supply pack is released. The positive x-axis is the direction the plane is flying, and the positive y-axis points downward. I'm telling you a coordinate system to use. Assume the horizontal and vertical components of the air resistance are proportional to the square of the velocities. This is underscored because this is not what we usually assume. We usually assume it's proportional to the velocities. This will make the problem more interesting, I think. Part A, you are to develop a system of differential equations and initial conditions to model this system for x of t and y of t. Clearly state any additional assumptions in your write-up. And then part B, using the appropriate model that you did develop in part A, and as engineers using accuracy to the nearest foot at the end of the problem, determine the horizontal distance the pack travels. The plane altitude is 1,000 feet above the ground. The plane's speed is constant at 300 miles per hour. The proportionality constant for air resistance is K is equal to 0.0053. And I say in the correct units. I'm actually telling you what the correct units are here in this write-up. They should be pounds per foot per second whole squared in the denominator. And let's see, and the pack weighs 256 pounds. And so that's what you're trying to find. And so that's problem number 2. In closing, now more than ever, time is precious. Each day must count. Do the math that will make you strong. And now more than ever, take care of yourself because self-care is important. And now more than ever, take care of each other because we're all in this together. God bless you all. Look forward to seeing you in class.